This video is meant just to work through some extra problems and do some more examples of logarithm equations. As you get started, go ahead and copy down the problem, pause the video, work through it at your own pace, and then turn the video back on to see the solution and see the problem worked out. So go ahead and pause the video. The goal when you have sums and differences is you want to combine them together into single terms. The other thing we notice about this example is that there are logs in every single term on both sides of the problem. So once we combine the plus sign into a product, the other side there's nothing to do, then this is a problem where log of x equals log of y, so x equals y, or log of this equals log of that, so this equals that. From here, this is a quadratic equation. You should be a master at solving these by now. Again, all of the ones in the book that I will assign will factor, so there's no need to do the quadratic formula or anything fancy there. When we check for domain, 3 and 1 both are fine here. 3 is fine here, 3 minus 2 is positive, but 1 minus 2 is an issue. So I know I have to mark 1 off the list. When I check 3 over here, 6 minus 3 is 3, so I know that I'm fine with 3, and 3 is my only solution for this problem. Okay, go on to the next one and do the same thing. All right, copy this problem down, pause the video, work it out, and then check your answer with mine. Just like last time, plus goes together as a product, so we have x squared minus x minus 6 after we combine our like terms. And again, we have logs in every single term on both sides of our equation. So that means if log of this equals log of that, then we can just set the expressions equal. This has to be equal to that, and we solve for x. Once again, we can factor. When we check our domain issues, 6 minus 3 is 3, that's allowed. 6 plus 2 is 8, that's fine. And 6 times 4 is 24, so that's okay. But notice if you use -1 in this expression or that one, and it only has to be bad in one place, but that would make me take the log of a negative number, so I can't use that one at all, which means 6 is the only solution here. Here's the next example. Notice that this one's different because I have logs in some of the terms, but not all of them. So when you pause the video, go ahead and think back to how we treated this one different. Now in terms of the first step is the same. Plus goes back together as times, and so we're going to FOIL this guy out and put the two log terms together into one. Now, I think I missed something on this. Nope. Yeah, this should have had a 2 also. You won't ever be given a problem where it mixes and matches bases. So that 2 needs to be there in all 3 steps. So now the difference comes in the fact that there's no logarithm on this side of the equal sign, which means instead of just being able to set stuff inside equal to something over here, then we had to go to our exponential form instead. So the base of this logarithm is 2, the exponent is 3, and we know 2 to the 3rd power has to be equal to the stuff inside. From here, when I have a quadratic equation, just like all the other quadratic equations, I'm going to subtract that 8 from both sides, get a 0. I'm going to factor, set each piece to 0, solve for x. Now when I check my 5 works in both places, it's fine. But -1 gives me log of -2 here, so without even checking it anywhere else, I know I have to mark it off the list. For this problem, the only solution is that x is equal to 5. for this last example. Once again, logs in some of the terms, but not in all of them. Most of your problems when you're combining your logarithm terms together will involve products, but again, if this is a minus sign, then that's a minus sign, then you need to put it together as a quotient instead. But on this one, when we FOIL, on the left and combine our like terms, then from here, we're going to go to our exponential form. So in this problem, the base is 3. I know 3 to the second has to be equal to this stuff inside, which I'm going to go ahead and rearrange and combine like terms. Negative 2x squared plus 3x plus 14. Now if I'm going to factor this thing, I need to get a 0 on one side. I like my x squared terms to be positive, so I'll add the 2x squared over. I'm going to subtract the 3x, and I'm going to subtract 14. So 9 minus 14 is negative 5. Then when I go to factor that, the two numbers that multiply to be negative 10 and add to be negative 3 are negative 5 and positive 2. So I will get the polynomial factored. I'll set each piece equal to 0, and I'll solve each piece for x. When I check, 7 minus 2 times 5 halves is 5. 7 minus 5 is 2. I'm in good shape there. 2.5 plus 2 more is positive, so I'm fine there. Notice that negative 1 plus 2 is positive. And if I take 7 minus 2 times negative 1, I'm really taking 7 plus 2 here, which is 9. Which means that even though that the x value itself is negative, when I plug it back into the expression, it is not. So that's why it's really important. Some students just mark off every negative answer. And with a lot of the problems we're given, that's the case, but not every time. So this one has two solutions, both 5 halves and negative 1.